In this lesson, we're going to talk about large sample hypothesis testing. Sometimes you'll see this referred to as z-test because we're going to be using normal distribution. In the first line of the notes here, I've denoted the parameters that are typically involved in large sample hypothesis testing. They're a single population mean, mu, a difference of two population means, mu1 minus mu2, a proportion, p, or a difference of two proportions, p1 minus p2. In follow-on videos, we'll do examples of a mean and also of two proportions. Let's talk about the assumptions. We're going to use random samples to collect data to make our inference. Remember, hypothesis testing is about taking empirical data, a sample, and using it to make an inference about a population. First assumption is that data will be IID independent and identically distributed. For the continuous case, that means our expected value will denote by mu. That's actually going to be the parameter we want to estimate. And our variance will be denoted by sigma squared. In the discrete case, our expected value is p. And again, that's the parameter we're going to want to make inferences about. Second assumption is that we have large data and that we can use the central limit theorem. In the continuous case, that means we must have more than 30 observations. That's fairly conservative. For most distributions, we can have less than that. But if it's greater than 30, even extreme distributions will look normal when we add up the random variables. The discrete case, we're going to have n be greater than 9 times p over q or 9 times q over p. And it depends. We're going to put in the numerator the larger. The larger of p or q goes in the numerator. Seems like an odd criteria, but it really comes from when we estimate the proportion. We want plus or minus 3 standard deviations around that estimate to be within the interval 0 to 1 because the proportion has to be between 0 and 1. Last criteria is the variance is known. That one is difficult. How would you know the variance but not the mean? Maybe from historical data, or what's common is we still end up using a sample mean and making the argument that as long as the sample is large enough, our hypothesis test is fairly robust to a violation of that assumption. Implications of some of these assumptions. Again, if we're going to use the central limit theorem, if we're going to make a inference about the population mean, we're going to typically use a sample mean, y bar. By the central limit theorem, y bar is going to be normally distributed with mean mu and standard deviation sigma over square root of n. And you can see the cases for the others as well. Again, notice that q is just 1 minus p. Alright, now let's talk about the procedure. First step in the procedure is we have to list our hypotheses. I'm going to use the notation of a capital theta to denote the parameter of interest. Again, what would that be? It would be mu, a population mean, p, population proportion, etc. The theta naught is actually the number that we're interested in. So we're making a claim. For instance, the average household income in America is greater than 55,000. Theta would be mu, the average household income. Theta naught would be 55,000. A couple things to note then. In the null hypothesis, we're always going to have the equality, and you'll see shortly why. The alternative is what we want to show or prove or verify, whatever the words are. In this case, I'm using a greater than in the alternative. It could also be a less than. Either of those two cases are called one-sided. The last type of hypothesis test would be an equality in the null and an inequality not equal to in the alternative. That's called a two-sided. So I'll continue with the example of a one-sided. Next step is we need our test statistic. In this case, it's going to be an estimate. I'm going to call it theta hat. we need the distribution of theta hat, and that's where the central limit theorem is going to come in for us, because that distribution will be normal. Third, we need to pick alpha. If you remember from our introduction to hypothesis testing, alpha is the probability of a type 1 error. That is, probability we reject the null given that the null is true. Typical values that people use for alpha is 0.05. That's sort of the de facto standard. And that comes from just our intuition that 5%, if something happens less than 5% of the time, that's relatively rare. We're comfortable with that number. Medical studies will typically have a number that's smaller than that, 0.01 or maybe even 0.001. For now, we'll use 0.05. Next step, we need to find the rejection region. This one is perhaps more easily illustrated with a picture. So what I'm going to draw here is a picture of the distribution of our point estimate theta hat. For our one-sided test, we're saying under the null, the value of that is theta naught. And it's going to have a normal distribution by the central limit theorem. Again, this could be y bar, mean, if we're making an inference about mu, the population mean. Our alternative value, which I'll use as subscript A, would be over here. Again, it's normal. And why did I draw it to the right? That's because under our hypothesis test, the alternative value of the parameter was greater than the null value. And as I said, this is the distribution of our estimate. What we need to do is find a value k. And this is our alternative hypothesis. This is our decision criteria. If we're to the right of k, if our sample statistics to the right, we're going to believe the alternative. If it's not, we're going to believe the null. So our job is to find k. So up here I showed you how you do that. You want to solve this probability problem. Probability of that point estimate being greater than k given the null, that is theta is equal to theta naught, has to equal alpha. And you'll solve for k. The last is you have to make a decision. If sample statistic greater than k, you reject the null hypothesis. If the sample statistic is less than k, fail to reject. You don't say you accept H naught, you say I fail to reject. Again, back to our criminal trial system, we don't say that the accused is innocent, we say not guilty. Right? Last, some notes on how to write up your conclusion. So what's important here is you're trying to convey information to a decision maker. A couple of things you need to have in your conclusion. First is you need to say that this decision was based on data. It's an empirical decision. So you can use the word evidence, empirically, based on data, but you're telling the reader that it was based on a sample or data. Second, you need to tell them the confidence level, what you picked for alpha. Remember, you picked alpha. Third, you need to tell them your decision, reject or fail to reject. And the last thing you need to do is use the context of the problem. So if we're talking about household income in America, you'll need to state that that's what you're making a decision about. And you also need to be clear what the parameter is, mean, proportion. Again, it's just to convey information to the reader. And that's it for this lesson.